Awesome. It's now 4:57. I will wait a couple minutes and we'll start right at 5. If you get here, please let me know you're here in the chat. Say hi. According to YouTube, there are 4 people here, but no one's yet said hi in the chat. Can you all see where the chat is, hopefully? Hopefully you can all hear. Shiva's here. Hi there. Shiva, is the sound working okay? Steven says no. What are you saying no to, Steven? Is the sound not working? Or are you saying don't let that stop you and you're responding no, sir? Hopefully that's it. Hi, Pablo. Okay, good. Glad to hear it, Steven. All right, it is now 5 o'clock and we'll get started. People will hopefully be joining us and jumping in, or maybe they'll watch afterwards. So I'm thinking I'm going to go through some of the basics to start with, so a little similarity and dilations. And then I'll look at section 8.1 in the text on right triangle trig and some of the word problems. And then I'll finish with a couple of the vector problems. Before we get started, is there anything anyone knows they would like me to cover? Any questions you had or problems that you were struggling with that you're sure you have a question on that I shouldn't miss? Otherwise, I'll kind of just go through things in general. Okay. So the book doesn't have anything on similarity and dilations, really. So those foundational standards, I gave you practice on Khan Academy, so I'll probably start with that. So I'm going to leave that screen and head over here. And this first problem says, draw the image of triangle ABC under a dilation whose center is point C and the scale factor is 2. So I can tell that, this is my triangle I'm supposed to move around, and I'm supposed to make a dilated new triangle, scale factor about point C. So clearly point C is going to stay where it is. Dilation takes every point to a new point that is further away from the center by the factor of dilation. But if the distance from the center is 0, then it will stay right at the center. And then here we have point A. So there's point A originally. And we're going to dilate point A so that it's twice as far from the center. Hi, Lindy. How's it going? So in order to do that dilation, we're going to say point A is up 4 and over 1 from point C. So I'm going to go up 1, 2, 3, 4, and over 1. And same thing with point B. Currently, point B is over 2 and up 1, 2, 3, 4, 5. So I'm going to go over 2 again and up 1, 2, 3, 4, 5. So there's the image triangle, triangle A prime, B prime, C prime, that's been dilated at about point C by a factor of 2. Sweet. I'll probably do one more of these, and then we'll be done. So here's a bigger triangle, point A. Oh, sorry, triangle ABC, and we're going to dilate about a center A. So again, A will stay at the center. And then we want to make it 1/4 as large. So all of the points will shrink towards point A by a factor of 1/4. So here's the original triangle ABC. And currently, to get from A to B, I would go over 12 and up 4. So 1/4 of that is over 3 and up 1. So the new point B prime is over 3 and up 1. Currently, to get from A to C, I would go over 8 and down 8. So 1/4 of that is over 2 and down 2. So there's my new triangle, triangle A prime, B prime, C prime, that has been dilated about point A by a factor of 1/4. Rockin'. Any questions about dilations all by themselves? Pablo, I was hoping you would have some questions about dilate. So if a point is at where they want us to dilate, that point stays at the same place. Yes, exactly. Perfectly correct, Pablo. The center of dilation will not move under dilation. That's exactly correct. But if no points were at the center of dilation, then all of the points would move. So let's say I did that same problem here, and instead of dilating about point A, I dilated about the origin. So I moved all of the points closer to the origin. Well, the negative 6, 2 would go to, well, 1/4 of 2 is a half. So I can't actually land it at a half. So that's not going to work. But if I was dilating about the origin, maybe by a factor of 2, then all of the points would move. So here's a dilation about the origin by a factor of, 1/2. Then every single point did move. Excellent. Easy peasy, good. Pablo's got it. Rockin'. Okay, now, why do transformations matter? Well, I was hoping to look at some problems where we're looking at the properties of dilation. So a dilation, let's see, this one's about point P by a scale factor of 2. And a dilation will take every point to a new point on the same line. That's true. Oh. A, D, and A prime. Oh, yep. No, none of those are true. There we go. So every point would move. Let's see. No, these aren't really what I was looking at. I'm interested in looking at dilations and similarity. So maybe let's go back to the questions about similarity. There we go. That doesn't have anything about dilations. Maybe the definitions of similarity. Similarity and transformations. That's what I was hoping for. So, in order for two figures to be similar, then there must be a dilation from one to the other. So we know that they're similar if we can get from one to the other using a sequence of transformations that might include dilations. And the properties of dilations lead us to the properties of similarity. Because all sides will be proportional after a dilation, similar figures have proportional sides. Because all angles will remain unchanged after a dilation, similar figures have congruent angles. So let's see if we can map triangle ABC to triangle DEF using translations, rotations, reflections, and dilations. So I'm going to start by translating point A to point D. Then I'm going to try rotating. This rotation tool has a little bit of trouble to it. That rotation isn't working. I was hoping to get a point to line up. There we go. Okay, then I'm going to try a reflection about that line that I lined up. Then I'm going to try a dilation about that center that I got to be the center. There we go. Ta-da. So that means that those two figures must be similar because the properties of translations, rotations, and reflections would mean that the triangles were congruent, and the properties of dilation mean that they're similar. The properties of those transformations lead to the properties of similarity between triangles. And the properties of similarity between triangles lead us to trigonometry. Cool. Any questions about some of the foundational pieces involving similarity and dilations? I think I'll maybe do one last one where because I think this will probably come up on the test. Let's look at similarity and solve for some sides. Cool. So here's a question where we have to look at what it means that they're similar. We know that one triangle is isosceles, so we can see because of the isosceles triangle and the fact that they're parallel that this must have been a dilation that occurred. And Shiva is asking a great question that I get a lot. On the test, are we going to have to answer questions that are just like the ones I just did? No. I make no guarantees that the review session is just like the test whatsoever. I try to cover things that I know I put on the test so that, you know, in the course of this review session, I think I'm going to cover some important ideas that are on the test, but I never do questions here in the review session that are really just like the test at all. So the concepts are the important concepts, but I don't do, it's not like this is a practice test and you're going to get the exact same questions. It's not like that at all. So I think this is good stuff. These are the right ideas. These ideas will be on the test, but it will not be true that you'll just see those same exact questions, like with different numbers. The questions that are on the test are not what are the questions that I'm going over here. But there will be similar triangles that you'll have to find sides in, like this. Cool. Awesome, Shiva. So we've got this triangle. We can see that they're similar. There must have been a dilation that could have taken FOR to FAN, and we're supposed to use the properties of similarity and dilations to figure out the length of AN. Again, there will be similarity in triangles and finding side lengths on the test, but not something just like this. So I can see that in this dilation, 7 must have become 10. Oh, I don't get to draw over the picture in this. That's annoying. So I can see that the ratio of dilation is a ratio whereby a length of 7 becomes a length of 10, and I want to know what will 11.2 become. So I'm going to write 7 to 10 equals 11.2 to x, and I'm going to cross multiply. So 7x equals 112, so that x equals 112 over 7. So now I'm going to close out of that and check my answer, 112 sevenths. What? They don't like the way I wrote my answer? Fine, I'll round it. 112 sevenths rounded becomes 16. There we go. Cool. So I think that's all I'm going to cover on similarity and dilations, because I think that's all that's going to come up on the test. So now I'm going to head over to the textbook, and we'll write on time. That's nice. I'm going to head over to the textbook and do some problems from there involving right triangle trigonometry. So first, grab a shot here on this side. Some of the basic stuff. And then grab some of the word problems. And we'll let that be it for now. Okay, so I'm going to start with some of these easy ones back at the beginning. Maybe a cofunctions of complementary angles problem from 19 through 28. Then maybe one of those word problems, and we'll move on to some vectors. Okay, so I'm going to start with, I think number 15 seems like a decent one. So here I have a right triangle. I have to find the third side and then find the 6 trig functions of the angle theta. So I'm going to start by finding side C. I'm writing that a squared plus b squared will always equal c squared. There's side A. There's side B. So that 1 squared plus root 2 squared equals c squared. So 1 plus 2 equals c squared. So 3 equals c squared. So c equals the square root of 3. Okay, now I'm going to find the sine of theta, the cosine of theta, the tangent of theta, the cosecant of theta, the secant of theta, and the tangent of theta. Okay, sine of theta is the ratio of the opposite side to the hypotenuse. We know what it is specifically in this triangle, but we know by the fact of similarity and dilations that this will be the same ratio for any angle theta, because for any angle theta in a right triangle, this ratio of sides will always be maintained. It could be 1 to root 2 to root 3. It could be 2 to 2 root 2 to 2 root 3. It could be 1,000 to 1,000 root 2 to 1,000 root 3. Don't I mean cotangent? Thank you, cotangent. Yes, I mean cotangent, Lindy. Much appreciated. Sweet. Okay. No matter what these actual sides are, this ratio for any angle theta in any right triangle, for any of the same angle theta in any right triangle will always be the same. Okay, so the ratio of the side opposite theta to the hypotenuse is root 2 over root 3, which I don't want to leave a radical in the denominator, so I'm going to times by root 3 over root 3, which is going to equal root 6 over 3. Okay, cosine of theta is the adjacent over the hypotenuse, which equals 1 over root 3, which, doing the same move of timesing by root 3, makes root 3 over 3. The tangent of theta is the opposite over the adjacent, which is, in this triangle, root 2 over 1, which just equals the square root of 2. The cosecant of theta is the hypotenuse over the opposite, which is root 3 over root 2, which I'm going to times by root 2 over root 2, so I don't leave a radical in the denominator, and I get root 6 over 2. Then the secant of theta is the hypotenuse over the adjacent, which equals, for this triangle, root 3 over 1, which just equals the square root of 3. And lastly, the cotangent of theta is the adjacent over the opposite, which equals 1 over root 2, which I'm going to times by root 2 over root 2, so as to not leave a radical in the denominator, and I get root 2 over 2. Cool. 6 trigonometric functions of theta. Again, those are functions for theta and that same angle theta in any right triangle because of the properties of similarity and dilations. Any questions on number 15? Okay, I think that's relatively straightforward. I'm going to check out, let's try one with a little inverse trigonometry. So let's try number 42. So on 42, we get to use this triangle, and then 42, this set of information. Let's see, I'm getting a question from Steven saying, do all 6 trig functions show up on tomorrow's tests? Let me check, Steven. I'll even answer that. Doesn't look like it, Stephen. I only see 3 of them, not all 6 on tomorrow's test. Okay. 42 is the one I'm going to do next. We've got this reference triangle with angles A, B, and you might call that angle C, but it's a right angle, and sides A, B, and C. And here we're given that B is equal to 4, B equals 4, and C equals 6. And we want to find angle A and angle B from that, and side A. So I'm going to start by finding side A. I'm going to write that I happen to know that A squared plus B squared equals C squared. And that means that A squared plus 4 squared will equal 6 squared. And that means that A squared plus 16 will equal 36. So that A squared will equal 20. So that A will equal the square root of 20, which means that A equals 2 root 5. Okay, I like Arendira's tip that you should focus on memorizing sine, cosine, and tangent. I'm going to make a slight edit that the secant, cosecant, and cotangent are the reciprocals of those 3. Cosecant is the reciprocal of sine, secant is the reciprocal of cosine, and cotangent is the reciprocal of tangent, which is, I think, what Arendira is getting at with the word opposite. Another way of thinking about the relations is that they're co-functions of the same, of complementary angles. So the sine ratio is the opposite over the hypotenuse. What's opposite to one angle will be the adjacent to the other. So you can just change the opposite to the adjacent in sine, and you get cosine. The tangent ratio is the opposite over the adjacent, because what's opposite to one angle will be the adjacent to the other. You can just change the opposite and the adjacent. You get cotangent, adjacent over opposite. The secant is the ratio of the hypotenuse to the adjacent, because you get because the adjacent of one angle is the opposite of the other, you can change that adjacent into opposite, and you get cosecant. You flip out the adjacent and the opposite, and you get hypotenuse over adjacent. So there's 2 ways of thinking about those relationships. One is as reciprocals, and the other is as co-functions. And I think those are both kind of opposite. So be careful with opposite. But then the real meaning of the word opposite is probably in the inverse. So you shouldn't try to memorize with the word opposite, because really the opposite of sine is inverse sine or arc sine. The opposite of cosine is inverse cosine or arc cosine. And the opposite of tangent is the inverse tangent or arc tangent. Arendira, aren't you glad you made your tip and sent me off on that one? But yes, many people do just memorize sine, cosine, and tangent and think of secant, cosecant, and cotangent primarily as the reciprocals of cosine, sine, and tangent. Well pointed out. Okay, I was working on this problem. I had just found side A. I now know it's equal to 2 root 5. And now I'm going to find angle A. So I'm noticing here that for angle A, the adjacent is 4 and the hypotenuse is 6. So the trig ratio, thank you, Arendira. The trig ratio of angle A that's going to be relevant, adjacent, and hypotenuse will be cosine. So I'm going to say that the cosine of angle A is equal to the adjacent 4 over the hypotenuse 6. And that means that the arc or inverse cosine of 4, 6 is equal to angle A. So I'm going to pull up my handy dandy calculator, which on my iPad is Desmos. And come back. So we're looking at the problem. And we're going to ask, what is the arc cosine of 4/6? So I'm writing inverse cosine of 4/6, and I'll switch it to degree mode and find out that it's 48.19. Angle A equals 48.19 degrees. And then I also want to know angle B. I could find it out by subtracting from 90, but instead I'll practice a little more trig pieces, so I can see from angle B that the opposite is 4 and the hypotenuse is 6. That's the sine ratio. So I'm going to write down here that the sine of angle B is equal to 4/6, so that angle B would equal the inverse or arc sine of 4/6. And if I do inverse sine of 4/6, it'll tell me that that other angle is 41.81. Angle B equals 41.81 degrees, which of course I could have gotten by subtracting from 90. Okay, any questions on a little right triangle trigonometry with some basic triangles? And halfway through the review session, we're halfway through the unit. Solid. I think I'll do a 30, 60, 90 problem, and then, or maybe I'll do a trig application problem here in 8.1, and then I'll do a 30, 60, 90 problem with vectors. That'll be good. So I'm going to leave this page and look at a word problem. So I'm thinking, let's see, where's a good word problem? Ooh, I like this one. Number 58. A security camera in a neighborhood bank is mounted on a wall 9 feet above the floor. So, wall, 9 feet, security camera. That's the camera. What angle of depression should be used if the camera is to be directed to a spot 6 feet above the floor and 12 feet away from the wall? So 12 feet. And there's this cool podium. I like to think of it in my head. It's like a jewel case. Right there. Well, maybe the jewel case. I'm thinking the jewel case is like right here. And the thief, that's a really bright jewel. And the thief that they're expecting is 6 feet tall, and they want to catch him on camera. So this is 6 feet here, and there's the jewel case, and here's the angle to the dude that they're going to catch. And they want to know what angle of depression should be used. So that means how much down from the horizontal should they point it to catch the guy on camera. So there's my diagram. And now to solve for theta, I'm thinking it's good that I know this adjacent length. So I'm going to write that in here. This is adjacent to angle theta, and it's still 12. And I should also look for that opposite length in this right triangle, and that's 3, because 6 plus 3 would make 9. And that's a right triangle. So to find theta, I'm going to say opposite over adjacent, which is the tangent ratio. Tangent of theta equals opposite 3 over adjacent 12. And that means that theta equals the inverse tangent of 3/12. And I'm going to pop up my calculator here. And say, what's the inverse tangent of 3/12? 14.03 degrees. Cool. Any word problem questions? I wanted to do one with like a north and a south. Let's check out bearing of a ship, number 64. Okay. Put my calculator away for the moment. Back out a little bit and grab just this one, number 64. No, I didn't grab it very well. Okay, here we go. The ship leaves the port of Miami with a bearing of south 80 degrees east. So I don't give you any. Isn't the 14.0? So Shiva is asking me a question. Let me go back. Shiva is asking me, isn't the 14.03 degrees above his head? This was the 14.03 degrees right there. It was how much should the camera be pointed down? What is the angle of the depression that should be used on the camera if the camera is to be directed to a spot right here? So this was the angle that I found, 14.03 degrees. Yeah, which is way over here at the camera. Saying if they started the camera out at dead level, that would be 0. But instead you should push it down 14 degrees to aim at the dude's head. Did I answer your question, Shiva? Okay, cool. Okay. So I didn't give you any bearings that look like this because we haven't talked about them, but I did give a problem, I think, that involves north, south, east, and west. So you do need to be able to set up north, south, east, and west. So here's north, south. Well, that's not south specifically. This is south, east, and west. North, south, and there's west, and there's east. And this problem says a ship leaves the port of Miami with a bearing of south 80 degrees east. So that means from due south 80 degrees towards the east, which would be over here. So that's where we're starting, where that's 80 degrees. From south, 80 degrees towards the east, and a speed of 15 knots. That means 15 nautical miles per hour. After 1 hour, the ship turns 90 degrees towards the south. That way. 90 degrees. After 2 hours, maintaining the same speed, what is the new bearing to the ship from port? So in 1 hour, we've got 15 knots. Going the same speed for 2 hours, they clearly went 30 nautical miles. All right. So first of all, I want to solve this triangle. I'm going to say, here's the new bearing to port. It would be that green dashed line. And I'd like to find this angle theta right here that I just will, well, I'm going to draw in purple, actually. So what's this angle theta? So right triangle, there's an opposite 30, there's adjacent 15. I'm going to write down that the tangent of theta must equal the opposite side 30 over the adjacent side 15, which means that theta will be equal to the arctangent of 30 fifteenths, which is obviously the same as the arctangent of 2, because what makes tangent a feature of the angle theta is the fact that those side ratios will remain constant for any angle theta, regardless of whether it's 30 to 15 or 2 to 1 or 4 to 2 or 1,000 to 500. That's why our calculator can tell us what the arctangent of 30 over 15 is. So I'm going in here, arctangent of 30 fifteenths is 63.43 degrees. So theta equals 63.43 degrees. And now what's this angle? Well, clearly it's 80 minus the 63.43. So this little angle in green, pull my calculator back up. $80 minus that is 16.57 degrees. So here in green, I have 16.57 degrees. Okay, which means that the bearing to the ship from port is south, 16.57 degrees east. That's the bearing along this green line. From south, 16.57 degrees towards the east. Now, you don't have to write bearings like this on your test. I just chose a problem that had north, south, east, and west in it because you're going to have a problem that has north, south, east, and west in it. You don't have to use these bearings, but you do have to know how to set up north, south, east, and west. Any questions about 64 and directions? Stefan Dagad. Special right triangles will definitely be on the test. Shall I switch over to vectors and special right triangles? That's what we're going to finish with. So I'm going to jump to section 9.4 and look for maybe a vector problem that has a special right triangle on it. So I can do both at once. So let's see. What do we got in terms of vectors and maybe one with a special right? Here's a whole group of them. That's perfect. I thought there was. Okay, so plus. So if you have your book out, I'm now on page 607. I took a big leap. I went over to the section on vectors, which is another additional or extended standard that's on your test. And I'm choosing to practice some vector problems that have special right triangles in them. So I think I'll do this till the end of our time together at 6. And Claudia says I should do a 30, 60, 90 triangle. I can do that. And Michelle says, yeah. Okay. I kind of read the comments because if people are watching afterwards, you can't actually see the chat anymore. The chat disappears. So that's why I read out loud the comments, even though you can all see them. So a 30, 60, 90 triangle. We did this one in class, but maybe I'll do it again because it's a nice starter and it won't be very long. And then maybe I'll do one of these other ones because all these ones, 57, 58, and 59, all have 30, 60, 90s as well. So let's start with 55. A vector V has magnitude 5 at an angle of 60 degrees. So the absolute value of vector V equals 5, and it's positioned at an angle from the horizontal of 60 degrees. And we're supposed to find the angle it makes with the positive x-axis. Oh, so we're supposed to find the component form, AI plus BJ. Component form of a vector is something that's on the test. So here we go. I want to know the component in x, which is the A component, and the component in y, which is the B component. So I'm going to write that A squared plus B squared equals C squared. I happen to know that because this is a 30, 60, 90 triangle, it's half of an equilateral triangle. So an equilateral triangle would look like that. So this has to be half of that side. So I'm going to write that A offhand must equal 5 over 2. So now I'm going to say that 5 over 2 squared plus B squared equals 5 squared. So that 25 quarters plus B squared equals 25. So that B squared equals 25 minus 25 quarters. So that B squared equals 100 quarters minus 25 quarters, now that I have a common denominator, and B squared equals 75 quarters. When I square root to find B, I get B equals 5 root 3 over 2. B equals 5 root 3 over 2. Now, hopefully you've memorized those ratios in a 30, 60, 90 triangle, so you know just offhand what to expect, that this is, if this was x, then this will be x over 2, and this will be x root 3 over 2. If this was x, then this would be 2x, and this would be x root 3. So now I have both a and I can write that the vector v equals 5 over 2 I plus 5 root 3 over 2 j. Any questions on that one? Okay, then I'll check out one we didn't do. Maybe 59, a nice 330-degree angle. So here's a coordinate plane, and there's the x-axis, and I've got 90 degrees, 180 degrees, 270 degrees, and 60 more degrees for 330 degrees. So there's my vector v going off that way at a 330-degree angle. (330 degrees). And the magnitude of vector v is 25. And I need to find the a component and the b component. So there's the a component along the x-axis and the b component along the y-axis. And I'm going to say I happen to know that a squared plus b squared does equal c squared. I know again that this is half of an equilateral triangle because it's a 30, 60, 90. And since it's half of an equilateral triangle, that means side B has to be half of this hypotenuse 25. So I'm going to write that offhand, I know that B equals 25 over 2. Is it helpful for me to do another Pythagorean theorem problem that derives this ratio? Or shall I just say I know, because I just did it last time, that this length will be root 3 times that length. So A will equal 25 root 3 over 2. Maybe I'll do it again. 25 over 2 squared plus some b squared should equal 25 squared, which means that, boy, 25 times 25, what is that? 625? 625 quarters plus b squared equals 625. So that b squared equals 625 quarters, 625 minus 625 quarters. So that b squared equals, well, that'd be 1250, so 2500 quarters minus 625 quarters, which means that b squared equals, gosh, stuff is getting hard, 1875 quarters, so that b equals the square root of 1875 quarters, which equals 25 root 3 over 2. Okay, and then I had to state the vector in the AI plus BJ form. And that means I've got A is 25 root 3 over 2. So I'm going to say the vector V is equal to 25 root 3 over 2 I hat minus, because B is going down, minus 25 over 2 J hat. Cool. That's 10 minutes to the end. Should we maybe talk about deriving the 30, 60, 90 ratios with variables and not numbers? I know you guys were talking about that a little bit, how it's easier with numbers but harder with variables. Let's do that. So here's the 45 degree, 90 triangle. And there's basically just two places I can put the X. I could put the x like this, and solve for this side c, which is the more common way to do it. And that gives me that x squared plus x squared equals c squared, so that 2x squared equals c squared, so that c equals the square root of 2x squared, so that c equals, I'm going to write it very clearly as the square root of x squared times the square root of 2, which is x root 2. So x root 2. So from there, I can find all of the trig ratios, right? Cosine of 45, sine of 45, tangent of 45, cosecant of 45, secant of 45, and cotangent of 45. And the opposite over the hypotenuse will equal x over x root 2. So cancel and cancel. So that equals 1 over root 2. So that equals, when I times to get the radical out of the denominator, root 2 over root 2. That equals root 2 over 2. Sine of 45 degrees is always root 2 over 2. Cosine is exactly the same. The tangent, opposite over adjacent, equals x over x equals 1, because cancel, cancel. Cosecant of 45 equals the hypotenuse over the opposite. So x root 2 over x, cancel, cancel, just equals root 2. The secant of 45 degrees is exactly the same, and the cotangent of 45 degrees is adjacent over opposite, x over x, cancel, cancel, just equals 1. Okay. And then let's try a 30, 60, 90 in the last 5 minutes. So there's my classic 30, 60, 90 triangle. 60 degrees, 30 degrees. I know that this is half of an equilateral triangle. So I'm going to draw in that equilateral triangle. If I were to make this length x, then obviously that would be x. Then obviously that would be 2x. And since this is equilateral, that would make this 2x. And that would make this 2x. So because a 30, 60, 90 is half of an equilateral triangle, the base has to be half of the hypotenuse. And then we can solve for the height using the Pythagorean theorem. So if I call this height side B, I will get x squared plus b squared equals 2x squared, so that x squared plus b squared equals 4x squared, so that when I subtract x squared from both sides, I find that b squared equals 3x squared. And when I square root, I find that b equals x. Well, let's write it out very clearly. The square root of x squared times the square root of 3. Because Lorenzo, now that you're here, I'll mention that we're distributing square rooting over multiplication, which we wouldn't do over addition. And yes, Michelle is absolutely correct. You can rewatch it. You don't get the live action questions, but you can see everything we did. And b equals x root 3. So I'm going to go in here and erase x root 3. And from there, of course, we can find all of the trigonometric ratios of both 30 and 60. So we can find the sine of 30 degrees, the cosine of 30 degrees, the tangent of 30 degrees, the secant, let's do cosecant of 30 degrees, the secant of 30 degrees, and the cotangent of 30 degrees, and the sine of 60 degrees, the cosine of 60 degrees, the tangent of 60 degrees, the cosecant of 60 degrees, the secant of 60 degrees, and the cotangent of 60 degrees. Okay, I think I might need a little more space. So let me adjust there. Whoops. And erase there. Okay, so the sine of 30 degrees is the opposite over the hypotenuse. So from 30, I'm looking at x over 2x. Cancel the x's. I get 1/2. For the cosine of 30 degrees, I get adjacent over hypotenuse, x root 3 over 2x. Cancel the x's. I get root 3 over 2. For the tangent of 30 degrees, I get opposite x over adjacent x root 3, x over x root 3. Cancel the x's for 1 over root 3, which I'm going to times by root 3 over root 3 to get rid of the radical in the denominator and get root 3 over 3. For the cosecant of 30 degrees, which is the hypotenuse over the opposite, I get 2x over x, cancel, cancel, for just 2. For the secant of 30 degrees, I get 2x over x root 3, cancel, cancel, for 2 over root 3 times root 3 over root 3 for 2 root 3 over 3. For the cotangent of 30 degrees, I get cotangent is adjacent over opposite, so x root 3 over x, which cancels again for just root 3. In the sine, we're going to have to do all of that on the test. Why can you cancel out both x's in the tangent and leave 2? No, I don't think there's a problem where you have to do all of that, Lorenzo. Yeah, I don't know who Cole the guy is, but he's definitely, it's probably Colin. Colin is saying that x over x equals 1. So right here, this x and this x cancel. Xander, what you're thinking about is if we had x over x squared, then the x and one of the x's would cancel and it would leave x. But x and x both cancel. I only have one x's. 2 times x cancels to 1/2. With me? It's torn. What's torn? Something torn? Oh, it's Tom. Colin is Tom. Oh, okay, cool. Okay, great. Thank you. Great. Call the guy is Tom. Now I'm with you. Alrighty, let's do sine. I'm going to move that way over here, actually, so I'm not so small. And let's move that same diagram over next to it. Okay, so for 60 degrees, why is 0 equal 1? Cosine of 0 equals 1. Ah, Tom, that is a question for next quarter. No, not really. Yeah, for next quarter. We can't really seriously answer that question until we get into the unit circle. Yeah, I have to leave that for now. What we have right now are definitions of the trig ratios for acute angles and right triangles. We don't yet have definitions of the trig ratios for non-acute angles. So we're just going to say for now that 0 is not an acute angle, and we haven't yet defined its cosine. So the definition we got was a right triangle trig definition for acute angles in right triangles. And we'll have to wait on 0 and 120 degrees and 1,000 degrees until second quarter. Okay. The sine of 60 degrees was the one we were going to do next. So now I'm looking at the 60 degrees. Opposite over hypotenuse is x root 3 over 2x. Xander, the x's are going to cancel again. And I get root 3 over 2. The cosine of 60 degrees is equal to the adjacent to 60 over the hypotenuse, which is x over 2x, which equals 1/2 when the x's cancel. Just a sec. Oh, hey, Emilio. The tangent of 60 degrees is opposite over adjacent. So x root 3 over x equals root 3 when the x's cancel. The cosecant of 60 degrees is the hypotenuse over the opposite. So 2x over x root 3. I hit it. Sorry, it's right there behind that wooden thing. Sorry about that. 2x over x root 3. X's cancel. You get 2 over root 3 times by root 3 over root 3. And you get 2 root 3 over 3. The secant of 60 degrees is equal to the hypotenuse over the adjacent, 2x over x, cancel, cancel, equals 2. And the cotangent of 60 degrees is the adjacent over the opposite, equals x over x root 3, cancel, cancel, 1 over root 3 times by root 3 over root 3, and I get root 3 over 3. Okay. I think that was it for my review session. I think we covered a lot of good stuff. Covered, I think, all of at least the content and the standards that are going to be on your test, unit test, tomorrow. I will definitely have fun at back to school night. Thank you so much, Lindy. Maggie is my partner, girlfriend, and I am going to 3D print a ring for her. That's what she's texting me about. Yeah, that was good. I think you guys had good questions. I'm excited. I'll see you tomorrow morning for a unit test. Is that a wild, Williams? I don't understand what that means. Oh boy. Anyway, I'll leave it there. And I'll talk to you all soon. Have a good night.